welcome to the deep dive. Today we're really breaking down a paper that feels like a foundational shift, a really crucial one, in how we train large language models, specifically turning them into, well, truly autonomous deep research agents.
Yeah, that's right.
We're going to zero in on this idea of Agentic Continual Pre-training, Agentic CPT, and the model that came out of it, Agent Founder. This deep dive is all about understanding why the standard ways of training just weren't cutting it for agents, and how this intermediate step really redefines things.
That context is absolutely vital, especially for our audience, people working right at the foundation model level. We've struggled for a long time with the limitations of, well, the standard post-training methods, your SFT, your RL.
Right, supervised fine-tuning and reinforcement learning.
Exactly. When you try to build sophisticated agents on top of these general-purpose foundation models, you hit a wall. The core issue, it's this optimization conflict. These general models, they fundamentally lack the necessary, let's call them agentic inductive biases.
The instincts, almost.
Yeah, precisely. The instincts needed to efficiently learn complex, multi-step stuff in dynamic environments. Post-training right now is forced to try and teach core knowledge and behavioral alignment at the same time, and that dual burden, it's just unsustainable, especially when you want to scale.
And the evidence, the technical proof that this CPT approach works, it seems pretty overwhelming in the paper. They detail how Agent Founder 30B, using this method, set new state-of-the-art performance across 10 benchmarks.
Yeah, the results are strong.
But that headline result, the one that really tells the story, is that remarkable 31.5% pass at 1 accuracy on HLE Humanities' last exam.
That HLE score is definitely the attention grabber. It signals something fundamental has changed.
So our mission today is to really dissect the methodology that made this leap possible.
Right. We're focusing entirely on Agentic CPT as this essential intermediate scaling layer. It's designed specifically to solve that foundational conflict we talked about.
So we need to get into the concepts, the data synthesis strategies. These first-order action synthesis, FAS, and high-order action synthesis, HAS methods, which sound really interesting.
They are highly scalable and, crucially, offline. We'll cover those, and then the rigorous empirical results that back it all up. Scaling laws, efficiency metrics, the whole picture.
Okay. And we're skipping strictly to what's in the paper. We should note the base models they used are from the Kuan 3 series.
Correct. Purely focused on the paper's contribution here.
Okay, let's start with alignment itself. Because the goalposts have really moved, haven't they? We used to talk about static alignment, making sure the output matched human preference in, say, a simple Q&A. But now you introduce tools, dynamic environments, and suddenly you need what the paper calls agentic alignment.
Agentic alignment is a whole different beast. It's orders of magnitude harder. It's not just about the final output. It demands the model maintains behavioral consistency with how a human expert would act, not just once, but across complex, changing situations.
The consistency in the entire process.
Exactly. The reasoning chain has to be sound. The choice of tools, the timing of invocations, that needs to be optimal. And critically, how does the model react when things go wrong? Like a tool fails or search results are unexpected, that adaptability is key.
And that's where the general-purpose models, the ones not trained with this CPT, just hit the ceiling.
Yeah.
Because they lack those agentic inductive biases you mentioned.
Right.
It's like, if you think about it, a general model might be a brilliant historian, knows all the facts. But an agent needs to be more like a detective. It needs the instincts for how to search, how to question sources, how to plan a multi-step investigation.
That's a great analogy. And that lack of instinct, that missing inductive bias, is what post-training methods like SFT and RL struggle so badly to install efficiently afterwards.
Okay.
Take SFT, supervised fine-tuning. It struggles because the space of possible agent behaviors, the policy space, is just enormous. Getting enough high-quality example trajectories to cover everything, basically infeasible manually. RL has its own problems here. Agent trajectories are often really long and complex. So the feedback signal, whether the whole thing worked or not, comes really late. It's coarse.
Right. Trajectory level of feedback.
Yeah. So the training often just defaults to making the model imitate specific successful paths it's seen, rather than developing flexible, robust decision-making skills needed for deep research. It gets brittle.
So if I'm an engineer trying to build one of these agents, the core tension I'm fighting is this simultaneous optimization problem. Post-training is trying to teach the core capabilities, the detective skills, and the high-level alignment, the follow-the-rules part all at once.
Precisely. That simultaneous objective creates this fundamental conflict, this inefficiency. The solution here, Agentic CPT, is to introduce a layer of pre-alignment. It aims to naturally support those agentic behaviors before you even get to downstream fine-tuning.
Ah, so it changes the problem structure.
It converts it from this low-efficiency simultaneous conflict into a progressive high-efficiency layering problem. The idea is the model enters SFT or RL already having those necessary detective instincts baked in.
Okay, that makes conceptual sense.
Yeah.
But that must require a very specific kind of training data for the CPT stage. What were the key principles they followed for building that data corpus?
Two main principles jump out from the paper. First, the data has to be incredibly broad. It can't be stuck in one application domain. Why? Because the underlying agentic skills, tool use, planning, reasoning need to be domain agnostic, universally transferable.
Makes sense.
Second, the training data needs to comprehensively cover various types of agentic behaviors. This is super important to stop the model from just, imitating or memorizing specific patterns it saw. You want to preserve, even enhance its ability to explore different behaviors later on.
All right, so let's look at how they actually integrated this into the training pipeline. The paper shows a new setup. It fundamentally changes the standard ABC flow.
Yeah, it's quite an elegant intervention, actually. You start with your base LLM, in this case, from the Kuan series.
Okay.
That base model then feeds into Agentic CPT Stage 1. Then, crucially, there's a second stage, Agentic CPT Stage 2. Only after both of those do you get to the more traditional final phases, general SFTRL and specific Agentic SFTRL.
So the key is inserting these two dedicated sequential CPT stages right after the base pre-training.
Exactly. That's the structural change.
And I'm guessing these aren't just one big data dump split in two. What are the strategic differences between stage 1 and stage 2? Especially around context length, that seems important.
Absolutely critical difference. Stage 1 is about volume and, let's say, initial acquisition. It churns through roughly 200 billion tokens, mix of agent data, general knowledge, reasoning stuff, and it operates within a pretty standard 32K context length.
Okay, 200 billion tokens, 32K context. What's the focus?
The focus is preliminary acquisition, getting the model familiar with basic agentic patterns. Simple tool calls, straightforward multi-step reasoning chains, recognizing the right formats, foundational stuff.
Got it. Then stage 2.
Stage 2 is about qualitative refinement. It uses a smaller amount of data, around 100 billion tokens, but this data is very carefully curated, high-quality agent data. And here's the kicker. They dramatically extend the context window to 128K.
Wow, 128K. That's significant.
It is, because the focus shifts here. It's about developing a sophisticated understanding of complex action spaces and, importantly, long-horizon planning strategies. You simply need that huge context window to see and learn from complete complex interaction trajectories.
Right. You can't learn long-term planning if you only ever see short snippets.
Okay.
But this brings up the resource issue. Generating 300 billion tokens of high-quality agent data. Normally, that means insane costs for live API calls, right? Web searches, code execution, databases.
That's the usual bottleneck.
Which leads us to the core of their scalability strategy. First-order action synthesis, FAS, and higher-order action synthesis, HAS. He said this is key for cost effectiveness.
It is the defining feature of their methodology, I'd argue. The really ingenious part is that both FAS and HARAS operate entirely without needing external tool invocations during synthesis.
Ah, completely offline data generation.
Exactly. They generate massive amounts of high-quality agent data entirely offline. This fundamentally breaks that cost and scalability constraint. Think about it. It replaces potentially millions, maybe billions of dollars in live API calls with a high-throughput, synthesized data generation process.
So it turns an expense problem into a data synthesis problem. Much more trackable.
Much more tractable. It's what makes Agentic CPT feasible at this kind of scale. So FAS. This is the engine for building those domain-agnostic capabilities. It's focused on generating the basic building blocks, the planning steps, the strategies for finding knowledge, the reasoning structure, all the stuff that needs to work no matter what specific task the agent is doing later.
Okay, so where does the raw material for FAS come from? The paper mentions discarded trajectories, old tool results, public stuff like Common Crawl. How do you turn that, static or messy data into something an agent can actually train on dynamically?
Yeah, that's a good question. They use a two-phase transformation. Phase 1 is about building what they call the entity-anchored open-world knowledge memory. Now, this is different from your traditional knowledge graphs, your KGs.
How so? KGs are usually quite structured.
Right. KGs often rely on fixed schemas, Here, they transform unstructured text into a memory where entities map dynamically to declarative statements, basically, facts about the entity. And crucially, they preserve details like temporal markers, original sources, even the original writing style. And they focus on increasing the density of statements per entity.
Why is that important? Preserving sources and style.
Because it ensures the memory continuously expands and aligns with how information actually looks on the internet. Messy, fluid, evolving. It's much better suited for an agent that needs to operate in the real world than a rigid, fixed schema.
That sounds much more robust and scalable. Yeah. Okay, so that's phase one, building the memory. What's phase two?
Phase 2 operationalizes that memory. It's called multi-style question synthesis. They sample clusters of entities from the memory, particularly ones with lots of statements associated with them.
Yeah.
And based on those statements, the system synthesizes diverse and challenging questions. Things like factual retrieval, yes, but also numerical computation, multi-hop reasoning that requires connecting dots between entities, and complex synthesis tasks. That high density of statements per entity implicitly creates these complex links, even without explicitly defining relationships like in a KG.
So it pushes the model beyond just simple lookups.
Exactly. It guarantees the questions are diverse, reliable, and importantly, novel things the model likely hasn't seen in exactly that form before.
The example they gave really drives this home. The one about Paris needing to link the Louvre visitor numbers, the e-scooter ban from 2023, the timing of the Paris Air Show, all to figure out that Riyadh Air was the specific buyer based on commitment balance.
That example is perfect. It shows you need multi-hop reasoning, fact-grounded synthesis, probably external retrieval simulated during training. It's a complex chain that FAS data aims to prepare the model for. Now, even with synthesized data, generating a full end-to-end trajectory for every single complex question, that would still be computationally expensive.
Right.
So the efficiency insight here is that the initial part of tackling a problem, breaking it down, figuring out what information you need, planning the first step or two, that initial analysis, actually provides really high-quality planning data on its own.
So focus on the beginning of the process.
And they found that the quality of that first-step reasoning strongly correlates with whether the agent ultimately succeeds on the whole task.
Okay, so what's the efficiency hack then? How do they generate this planning data?
Instead of generating one full trajectory per question, they generate k diverse reasoning action data points for k different questions. These questions all share the same underlying knowledge memory but differ in style or focus.
And this is all offline. No API calls needed.
All offline. This lets them massively expand the exploration of different planning actions and cover more context, much more cheaply than simulating full trajectories.
But if an LLM is generating these planning steps, how do you ensure quality? It might generate nonsense plans.
Quality control is critical. They use reject sampling with knowledge alignment verification. Essentially, another LLM acts as a judge.
An LLM judge.
Yeah. It evaluates the generated reasoning chain and the proposed actions and estimates the probability that this plan will actually lead to acquiring the necessary knowledge. If the probability is too low, the plan gets rejected.
So it filters out the bad plans before they get into the CPT data.
Exactly. Ensures only plausible, high-quality planning data makes it into the training corpus, preventing the base model from learning flawed strategies.
Okay, so FAS also needs to handle the end of the process, right? Where the agent has gathered the info and now needs to synthesize it into a final answer or report. This sounds like a core skill for a deep research agent: logic, inference, grounding in facts.
Absolutely. And to really strengthen the synthesis skill, they use a specific two-step scheme for generating logical reasoning data. And again, critically, no external tools are allowed during this synthesis process.
2 steps. How does that work?
Step 1. The model first decomposes the question and generates a preliminary answer. Let's call it A1. This answer is based only on its internal knowledge and whatever initial thoughts or speculations it has.
Okay, so an initial draft.
Right. Step 2. Then the model is given the question again, plus the specific requisite knowledge it should have gathered, which FAS knows from the memory. Using this knowledge, it refines A1, corrects any logical errors, and generates the final answer, A2.
Why separate it like that? Why not just give it the facts up front in step 1? Seems simpler.
It seems simpler, but the motivation is subtle. They want to simulate a more authentic, reflective thinking process. If you just give the model all the necessary facts right away, it tends to learn to just mechanically slot them in as intermediate steps. It becomes an artifact of the input format, not real reasoning.
I see. By forcing it to generate A1 first, based on internal knowledge, and then refine it using the provided facts.
Exactly. It simulates a more genuine process of drafting than correcting and grounding. It prevents the model from becoming dependent on just plugging in facts, hopefully leading to stronger intrinsic reasoning abilities.
And then, I assume, more quality control.
Yep. Reject sampling again. They verify that the final answer A2 actually aligns with the ground truth answer for the question, validating that the whole two-step reasoning process was sound.
Okay, let's switch gears to high-order action synthesis, or HASE. This seems focused on getting more value out of the data, especially trajectories that might otherwise be thrown away.
That's a good way to put it. The big challenge in standard post-training is that if a trajectory doesn't reach the final goal, even if some steps were good, the whole thing often gets discarded. You lose potentially valuable learning signals from those intermediate steps.
Right, because the feedback is usually just pass-fail for the whole trajectory.
Exactly. So the goal of HATES is to shift the training objective, move away from just imitating successful trajectories and focus on optimizing stepwise decision-making.
Okay, stepwise. How does HASE achieve that? The paper mentions figure 5 and step-level scaling.
The core idea is that every single step within a long, complex trajectory represents a distinct reasoning state. And at that state, there's usually a whole range of possible actions the agent could take, not just the one it actually took. HASE wants to explicitly leverage this hidden decision process at each step.
So component 1 is step-level scaling. How does that actually work? How do you turn one step into many options?
That's pretty clever. For any given step, $6 in the original trajectory, happening within context dollars, they use other LLMs to generate $1 alternative thought and invocation candidates. Let's call these ALT-dollar.
Alternative paths the agent could have taken at that point.
Right. Plausible alternatives, maybe even good ones, maybe suboptimal, maybe just different reasoning paths. These non-dollar alternatives are then merged with the original step Astara step, which is implicitly marked as the correct one from the original successful trajectory, if it was successful. Then they shuffle this combined set into a sequence tilde k.
So for each step, the model now sees the original action plus n alternatives all shuffled up.
Exactly. Suddenly, a single data point from the original trajectory is transformed into a rich decision-making scenario. Across the whole trajectory of length k, you've created the space of potentially $1 plus 1 times k reasoning actions. It forces the model to actively consider alternatives at every step.
Wait, you said HASS also uses suboptimal trajectories, ones that failed,
Yeah.
and it's adding these potentially divergent candidate actions. Isn't there a risk of teaching the model bad habits or reinforcing inefficient paths if you just present all these options? How does it learn which path is good?
Excellent question. That's precisely where component 2 comes in. Contrastive decision action synthesis. This provides the necessary supervision.
Okay, how does that work?
They transform this expanded trajectory with all the alternatives into an explicit step-by-step decision-making process for the model during training. At each step to dollar, the model is forced to explicitly output its choice. Something like, I will choose option dollars, where $dollars is the index pointing to the correct original step from the trajectory being analyzed.
Okay, so it has to pick the right one out of the shuffled list.
Yes. And immediately after outputting its choice, it sees the corresponding actual tool response, $dollars, from the original trajectory. But here's the crucial supervisory part. At the end of the entire synthesized trajectory, they append a final binary judgment. My decision is...
And they correct.
It's based on
the final success or failure of the original trajectory that this step was taken from.
Ah, I see. So even if the original trajectory failed, the model learns at each step to identify the action taken in that trajectory, and it gets the final signal that the overall path was incorrect. If the original trajectory succeeded, it learns to pick that step's action and gets the final correct signal. Exactly. The explicit choice output, I choose option N, combined with that final trajectory level judgment, acts as a powerful contrastive supervisory signal. It forces the model to learn to discriminate between good and bad reasoning paths at the step level, even when using data from failed trajectories.
That's really clever. It means you can reuse so much more data that was previously just digital waste because the final outcome wasn't perfect.
Precisely. It dramatically improves sample efficiency. It prevents overfitting to just one specific golden path trajectory pattern and helps the model learn more robust, generalizable decision-making skills by considering alternatives and learning from mistakes, both its own synthesized ones and the ones in the original suboptimal trajectories.
Okay, so I've got the theory. Agentic CPT with FAS and AS data. Now for the payoff. The empirical results. RQ1 in the paper. Agent Founder 30B seems to show, well, dominant performance across these 10 benchmarks.
Yeah, the overall picture is very strong.
The main finding seems to be It's superior to existing open-source deep research agents, and importantly, it's starting to seriously challenge some established commercial models in this space. And we should probably focus on pass at one accuracy success on the first try, no interventions.
Right. Pass at 1 is the toughest metric. Let's look at the general web search benchmarks first, table 1 in the paper. The gains are pretty immediate and robust there.
Okay.
On BrowseComp-en, the English version, Agent Founder 30B hits 39.9% pass at 1. That's a solid 10% absolute gain over the next best open source competitor mentioned, DeepSeek v3.1, which is at 30.0%.
A 10% jump is significant. That really suggests the CPT methodology is successfully embedding those core search and reasoning strategies.
It definitely validates the foundation. We also see Agent Founder 30B getting the highest reported single-agent accuracy on the GAIA text subset, 72.8%, and it leads on Xbench Deep Search with 73.0%. Pretty consistent leadership on the general benchmarks.
Okay, but what about the nuance? The paper mentions the Chinese benchmark, BrowseComp-en. How did it do there?
Right, that's an important point to address for a balanced view. On BrowseComp's, Agent Founder 30B scores 43.3%, which is, a decent score in absolute terms.
Oh,
but it is behind DeepSeek v3.1 at 49.2%, and notably behind OpenAI 3 at 58.1% on that specific benchmark.
Interesting. Does the paper offer any hypotheses for that gap?
They do. They suggest a couple of possibilities. One is straightforward. Maybe the proportion of Chinese data in their 300B token CPT corpus wasn't as high relative to English. The other hypothesis is more intriguing: potential suboptimal performance or even inherent bias of the underlying search tool they used, Google Search, when operating specifically in Chinese language contexts.
So the agent might be strong, but the tool it relies on could be the bottleneck in certain domains or languages.
Exactly. It highlights that even with a powerful foundation model, external factors like tool performance can still constrain the final agent performance. It's not operating in a vacuum.
Okay, good point. Now let's turn to the scenario-targeted web search benchmarks in Table 2. This seems to be where the deep research capability really shines, especially HLE, humanity's last exam. That benchmark is designed to be incredibly difficult, testing human-level reasoning and research skills.
Yes, HLE is considered one of the ultimate tests right now. And the big news here is Agent Founder 30B is the first open source model to break that 30-point barrier. It achieved 31.5% pass at 1.
31.5% on HLE. That feels like more than just another number on a leaderboard.
It really is. It's a critical validation of the whole Agentic CPT concept. To put it in perspective against closed source competitors mentioned in the source, Agent Founder, using this intermediate pre-alignment, is now empirically outperforming dedicated commercial products like Gemini Deep Research, which scored 26.9%, Kimi Researcher, also 26.9%, and OpenAI Deep Research at 26.6% on this specific super hard task.
Wow, so the CPT Foundation is providing uniquely superior generalization for these really knowledge-intensive, complex reasoning problems.
That's the strong implication, yes. It seems to unlock a level of capability that maybe simple post-training on a general model struggles to reach for these complex research tasks.
And beyond just beating competitors, the model shows strong practical utility too, right? Like for academic work.
Definitely. Its value as a potential academic assistant is highlighted by a state-of-the-art score of 75.3% on the academic Browse benchmark.
And what about tasks requiring synthesizing information from multiple angles?
It excels there too. On the Frames benchmark, which tests multi-perspective reasoning and consistent information synthesis, it achieved a superior performance of 89.6%.
Okay, and finally, it's not just giving single right answers, it's generating comprehensive outputs.
That's confirmed by the Deep Research Bench results. It achieved 47.9% on RACE-E overall, which specifically evaluates the quality and comprehensiveness of generated research reports. This score surpassed all other open-source agents and even OpenAI Deep Research on that metric. Of course, strong headline results are great, but we need to validate the method itself. That's where the ablation studies come in RQ2, 3, and 4. First up, RQ2, adaptability. The question is, does this Agentic CPT base model provide a better starting point regardless of how you fine-tune it later?
Right. Is the foundation itself better? Table 3 in the paper seems to address this by comparing the original Qwen 3 base model against the Agent Founder base, using 3 different downstream SFT methods labeled A, B, and C.
Exactly, and the finding is pretty clear-cut.
Agentic CPT gives consistent, substantial improvements across the board, no matter which SFT approach they tried.
That's the key takeaway. They observed average performance gains ranging from 5.75% with SFTA all the way up to 6.45% with SFTC, just by starting with the CPT-enabled agent founder base instead of the standard Quen 3 base.
So it strongly validates CPT as kind of universal pre-alignment step that makes subsequent fine-tuning easier and more effective.
Yeah.
It stabilizes things.
Yes, stabilizes and accelerates. However, there's an important nuance the analysis revealed. Post-training data, the specific SFT data you use, still matters a lot for unlocking the model's full potential in a specific area.
How did they see that?
Well, for instance, on that BrowseComp-zh benchmark we discussed earlier, the agent founder model fine-tuned with SFT configuration B outperformed the one tuned with SFTA by a significant 8.5%, even though both started from the same strong Agentic CPT foundation.
Ah, okay. So the CPT gives you a much higher starting line, a better foundation. But the quality and specificity of your final alignment data, your SFT data, still determines how high the agent can ultimately jump in specific domains.
Precisely. Which might also explain another observation they made about domain specificity.
What was that?
Information retrieval tasks like the BrowseComp benchmarks seem to benefit more directly from Agentic CPT compared to the really knowledge-intensive tasks like HLE.
So CPT is maybe really good at embedding the tool use and planning aspects.
That's the hypothesis. It strongly embeds the agentic process. But perhaps future research could focus on enhancing the base model's intrinsic knowledge comprehension even further during the CPT phase itself, especially for tasks like HLE that rely heavily on recalling and reasoning over vast internal knowledge.
Okay, that makes sense. Let's pivot to RQ3, the impact of training strategies. This looks at Table 4. We know CPT works, but did they really need that complex two-stage approach with the super long context in Stage 2, or was that just overkill?
A very fair question. Is the complexity justified? The finding here is pretty definitive. Yes, the two-stage configuration is essential.
How'd they test that?
They compared it directly against a single-stage CPT approach. Critically, they used the same total amount of CPT data, 50 billion tokens, and the same SFTA fine-tuning afterwards. The only difference was one model got the data in 2 stages, with Stage 2 using 128K context, and the other got it all in one go, presumably at the shorter 32K context.
And the result?
The two-stage agent founder, the one that incorporated that synthesized long context data in Stage 2 with the 128K window, consistently performed better. An average improvement of 3.3% on pass at 1 across the board.
So it confirms you really need to train on complete long context agent data. Just feeding truncated sequences, even lots of them, isn't enough for these complex long horizon tasks.
Exactly. That longer context window seems crucial for the model to effectively connect complex, multi-step actions to the final goal or outcome. It justifies the added complexity and resource cost of that second stage.
All right. And finally, RQ4 looks at the data types themselves. Table 5 compares using only the first-order action synthesis, FAS data, versus using the combination of FAS plus the high-order action synthesis, HAS data.
Right. This validates the different roles we discussed earlier. FAS data alone, focused on planning and reasoning, showed substantial gains. For example, on BrowseComp-zh at 3, just using FAS improved performance by 9.0%. That proves FAS is effective on its own for building those core planning reasoning structures.
But adding HAS helped even more.
Yes. The combination of FAS plus HAS provided complementary, positive gains across the benchmarks. It wasn't redundant. This confirms that HAS, by reorganizing supervision signals around contrastive decision-making and reusing those suboptimal trajectories, strengthens the agentic foundation in a distinct and beneficial way. It adds something different than just the planning data from FAS.
Okay, scaling. This is often where the rubber meets the road. If Agentic CPT is truly a superior foundation, we should see that reflected in how well the performance scales with model size and data volume. Figure 6 in the paper seems to cover this.
Let's start with model size. The scaling trend itself is pretty consistent and, frankly, expected. Average accuracy across tasks climbs steadily as the model gets bigger. From 20.4% for a 1 billion parameter model to 32.7% for 4 billion, and hitting that peak of 48.9% for the 30 billion parameter agent founder.
So bigger models do perform better. No huge surprise there for complex tasks.
Right, and complexity needs capacity. But the critical finding here isn't just that it scales, it's the scaling efficiency. Agent Founder 30B, at 48.9% average accuracy, actually exceeds the performance of larger baseline models mentioned in comparisons, like DeepSeek v3.1, which is larger but scored 43.0%, and Kimi K2, also larger, scored 29.6%.
Hold on, so the 30B agent founder is outperforming larger models that didn't use Agentic CPT.
On these agentic tasks, yes. That's a massive finding for efficiency. It strongly suggests that Agentic CPT acts like a multiplier for model capacity. It allows a smaller model to achieve superior agentic performance because its parameters, its capacity, are being utilized much more effectively for the specific reasoning and tool use skills required.
That has huge implications for training cost and deployment. You might not need the absolute biggest model if you can make a smaller one smarter with CPT.
Precisely the implication.
Okay, what about scaling with data? Does more CPT data always mean better performance?
The paper validates the familiar logarithmic scaling law here. You get the biggest bang for your buck early on. The most rapid, substantial improvements, a 3.8% absolute gain in average accuracy, happen within the first 15 billion tokens of CPT data.
So the model picks up the core agentic instincts quite quickly and efficiently from the CPT data.
It seems so. But importantly, the benefits don't completely plateau. And remember our discussion about the two-stage CPT.
Yeah, with a long context in stage 2.
The benefits of that stage 2 CPT using the 128K context persist even as the main scaling curve starts to flatten out at higher data volumes. For instance, they saw a 1.8% gain from stage 2, kicking in around the 65 billion token mark, and still a 1.0% gain way out at the full 315 billion tokens.
So even when improvements get harder to come by, that long context refinement stage still delivers value.
Exactly. And overall, the model showed robust, sustained improvements across the entire 315 billion token CPT budget, achieving a total cumulative gain of 8.0% from start to finish. It validates the whole methodology across a very large data scaling range.
Now, one of the theoretical goals of CPT was to make downstream fine-tuning, SFT, easier, right? To alleviate that dual burden of learning capabilities and alignment simultaneously. Does the training process itself show evidence of this? Figure 7 looks at loss convergence.
It provides exactly that technical confirmation. They compared the SFT loss curves for the agent founder models, trained with varying amounts of CPT data, against the baseline Qwen 3 model, all being fine-tuned on the same downstream agent tasks. And the results are stark. All the agent founder variants achieve markedly lower final SFT loss values compared to the baseline. The best performing one, the model trained with the full 315B CPT tokens, reached a final SFT loss of 0.7953. The baseline Qwen 3 model, starting without CPT, ended up much higher at 0.8656 on the same task.
So that raw number difference, 0.7953 versus 0.8656. That's the empirical proof that CPT sets the model up better for SFT. What does that mean practically for someone training these models?
It means less wasted compute during SFT, potentially faster convergence, and likely more predictable, reliable training outcomes. It confirms that CPT is effectively doing its job, pre-endowing the model with those foundational agentic capabilities, which makes the final adaptation to specific agent tasks smoother and more stable. Seeing the loss consistently decrease with more CPT data confirms you're building a better initialized, more stable base.
The paper also digs into some deeper technical analysis, like how CPT affects mixture of experts, MOE architectures. What do they find there, looking at figure 12?
Yeah, this was an interesting observation specifically on the MOE models. They looked at how different experts within the model were being activated during a task. BrowseComp-zh in this case.
And what changed after CPT?
After Agentic CPT, the distribution of which experts were being used became significantly more balanced, especially in the later lowers of the model compared to the baseline.
More balanced expert usage. Why is that good?
Well, seeing a more balanced activation pattern is almost like a technical fingerprint of a healthier, more robust MOE model. It suggests CPT didn't just teach the model new facts or skills, it might have fundamentally rewired how the model distributes computation across its experts. This leads to more diversified utilization, less reliance on just a few hero experts, and importantly, it helps mitigate the risk of dead experts, parts of the model that don't get trained effectively. Empirically, this usually translates to greater training stability during the SFT phase.
Interesting. So it's not just what it learns, but how it learns and utilizes its internal structure. Okay, one last crucial check. These capabilities learned for deep research tasks, do they actually transfer to more general agentic tasks?
That's the million-dollar question for generalization. Table 6 addresses this. They tested Agent Founder 30B against the baseline Quen 3 model on a general agent benchmark called AC Bench.
And the result?
Agent Founder 30B outperformed the baseline here too, scoring 70.0% versus 67.2%. It's not a night and day difference, but it's a clear improvement.
So that suggests the planning, reasoning, and tool use efficiencies learned via Agentic CPT aren't just narrow skills for research. They do seem to transfer, at least to some extent, to a broader range of agent tasks.
Exactly. It supports the idea that Agentic CPT is building a more general-purpose agentic foundation, not just a specialized research agent foundation.
Okay, let's bring this down to the concrete level. How does the agent actually behave in practice? The paper analyzes tool call patterns in Figure 8, and it seems the agent adapts its strategy based on the task.
Yeah, this shows some nice adaptive calibration. For the really complex research tasks like BrowseComp-en and especially HLE, you see these heavy-tailed distributions for tool calls.
Meaning
Meaning the agent frequently needs to make a lot of tool invocations, lots of web searches, lots of thinking steps between searches. Persistence is key. It needs high tool density to dig deep, combine reasoning with search, handle ambiguity.
Okay. And for simply more structured tasks?
For tasks like WebWalker or GAIA text, which have more well-defined problems and maybe clear paths to a solution, the agent employs much more conservative tool usage. The distribution peaks very sharply at low invocation counts, maybe just 1 or 2 calls. It doesn't waste time searching extensively if the problem doesn't demand it.
So it's not just blindly calling tools, it's adjusting based on perceived task difficulty. Now, Figure 13 connects tool usage to accuracy. What does that tell us about efficiency?
This analysis gives some critical insights. First, efficiency. Tasks that get solved with fewer tool calls, specifically in the 1 to 8 turn range, generally achieve the highest accuracy, hitting about 81.3% success.
So good initial planning leads to quick, accurate solutions. Makes sense.
Right. Second, tool necessity. Accuracy drops quite noticeably, down to 66.7% when the agent makes 0 tool calls. This really underscores how vital the web search capability is for these deep research tasks. The agent can't just rely on internal knowledge alone for many of them.
And what about the really complex cases? The ones requiring tons of tool calls?
This is where the deep part comes in. Even for the really challenging cases, the ones requiring over 40 tool call turns, the model still maintains a non-trivial success rate averaging around 17.5%.
So even when the problem demands an incredibly long and complex investigation, the agent doesn't just give up. It has the persistence and capability to follow through, sometimes successfully, even after 40-plus steps. That is deep research capability.
Exactly. That ability to handle extreme complexity is a key differentiator.
Let's loop back to that Paris Air Show Louvre Riyadh Air example we discussed under FAS. The paper includes a case trajectory. How does that illustrate this need for depth and the success of CPT?
That case study is the perfect, practical illustration of why CPT is needed and why it works. To get that final, fact-grounded answer about Riyadh Air, the agent had to execute something like 50 distinct steps.
50 steps, wow.
Yeah, a long chain. It involved researching the Olympics' impact on Louvre timing, connecting that to the 2023 e-scooter issue affecting transit, using that temporal context to pinpoint the biennial air show, searching for specific orders placed there, comparing commitments. It's a complex web.
And this kind of extensive, fact-driven investigation, requiring high tool density and persistent reasoning over many steps,
it only succeeds because the Agentic CPT process embedded the fundamental capability, the bias, to plan and execute such a long, complex sequence right from the start. A standard model without that CPT foundation would likely get lost or fail much earlier in that chain. #tag outro. So to wrap things up, the core contribution here, the big takeaway from the Agent Founder paper, is really the successful introduction and validation of Agentic Continual Pre-training Agentic CPT. It establishes it as this necessary intermediate step, sitting between general pre-training and the final downstream tuning.
And critically, they made it scalable.
Exactly. Made scalable and efficient through that systematic methodology using synthesized offline agentic data. You had FAS providing the scalable planning and logical reasoning data.
And HPs providing the contrastive decision-making signals and efficiently reusing trajectory data.
Precisely. Building that pre-aligned foundation offline.
And the empirical results really seem to confirm its necessity. Agent Founder 30B didn't just set a new SOTA among open-source agents, crucially beating proprietary models on tough tasks like HLE, but it also showed that superior scaling efficiency and better fine-tuning stability compared to the baseline. It feels like fundamental proof that embedding these agentic reasoning and tool use capabilities right at the foundational pre-training level via CPT is the right direction for building truly robust, deployable research agents.
I think that's a fair assessment based on the evidence presented.
So given this really robust monotonic performance improvement they saw with data scaling, and especially that superior efficiency where Agent Founder outperformed larger baselines on both general agent tasks and deep research tasks, it leaves us with a really interesting question to ponder, doesn't it?
Where do you think it leads?
Well, what's the theoretical limit here? How far can we push agentic capabilities purely through these targeted CPT methodologies? And, maybe more profoundly, how might this newfound efficiency in utilizing model capacity actually redefine how we think about the optimal trade-off? The ideal ratio between model size and data budget needed to develop the next generation of truly general-purpose capable agents. It feels like CPT might change that calculation significantly.